All right, so sorry about that delay. This is the first time using this room. Long story short, another class got scheduled at 4760 when we were going to hold stuff, so we'll just be having to deal with this room. But yeah, should be a cool experience. Yeah, welcome back, everyone. For those who are returning, or if you're new to ACM Cyber, well, welcome to the first Cyber Academy of this quarter. Um, just to kind of get started, just a quick reminder, we'll generally be holding the meetings in roughly this kind of format. Just start with some weekly announcements just to make sure you're up to speed about the events that we have for the next couple of weeks. Sometimes we will have some sort of speaker. This can be officers in the club. This could be members of the club. I sent out announcements a few weeks ago now. If you're interested in giving a talk for the club for any cybersecurity or honest, vaguely or actual cybersecurity, feel free to submit that form, and we're happy to have you guys give a talk to the club. Spend maybe 20 minutes doing that, and then spend the rest of the time working on our workshops. So yeah, jumping into announcements. So first announcement is we will be having our nail painting social tentatively planned for 24th of January, which I believe is a Saturday. This will be at 6 p.m. at 631 Shelton. Cyber Academy, we will not be holding cyber events in general on holiday weekends, so we will not have a Cyber Academy next week, but we will be holding it the week after on week 3. And I think we have another holiday, President's Day, I believe, in like week 7. We will also not be having Cyber Academy for that. We will also be holding our first Cyber Lab. So if you're interested in the CCDC or the Splunk Lab, make sure to submit the join form, which we'll talk about in a bit. And that will be in this room again on Wednesday. And then cyber basketball, is that still being held?
Yes.
Okay, so yeah, if you are interested in playing some basketball with some people here in cyber and other people I think also show up, that's Friday, 6 to 8 p.m. at the Hitch Course. Since it's the beginning of the quarter, I'll give my spiel. Please submit our interest form. That's how we know who's interested in doing what in the club for the quarter. And this also gets your name into our system so we know you've attended or at least expressed intention to attend ACM Cyber. And what will happen is you do the whole quarter, you have fun, do write-ups, do challenges, learn a lot. And then at the end of the quarter, there'll be another membership requirement submission form that you can fill out where you just say, oh, I've done and met like the basic requirements. And at that point, you'll be considered an active member. So since you're here for Cyber Academy, all you need to do is show up for most of the Cyber Academy workshops and then just quickly write up like how you solved one of the challenges from Cyber Academy. We'll even have like a dedicated kind of writing session usually on the very last Cyber Academy. So don't feel like, oh, I don't know how to start to write the solution. Yeah, pretty straightforward and hope you learn a lot. Yeah, without further ado, Arnav will be talking about very fancy HTTP stuff. So yeah, ma'am. So, yeah, hello everyone. I'm Arnav, one of the officers here, and today I'll be talking about exploiting race conditions, which is, I'll talk about what that means, but it's a type of bug in web applications and some special ways to make your exploits work better using the HTTP protocol. So the first thing you have to understand about my talk today is HTTP, which is kind of like the most important application layer protocol for web networking in this context for web applications. Basically, it's a protocol to access web resources. It's on the application layer, so it's kind of like the highest layer of the network stack. And how it works is that it's a client-server model, so clients will send requests to a server, and the server will provide responses. HTTP runs over TCP. TCP is transmission control protocol, so it ensures reliable data transfer. So basically, anything you send over HTTP will for sure be received by the server. You have like a guarantee of that, and it should be received in order. And for that, you need to open and close connections each time, or in general, to send HTTP requests, you need to open and close TCP connections. So you open a TCP connection, you send your HTTP data in there, and then you close the connection. A HTTP message contains a header and a body. Headers contain metadata about the request, and bodies, which can be empty, contain the actual data of the request. So this is more details on how the protocol works. So in an HTTP message, you first start with like a line that says like post or get. So anything, it's basically like telling you where you want to go, where you want to visit, what method you want to visit that resource with. So some methods are get, post, etc. and then the version of HTTP you want to use. That's what the request does. And then the request also has headers. Those are some of the headers. There's not very important to talk about today, but I guess one important header is a content length. So it tells you how much data is in the body. And then the body is kind of like the body of the request, like any actual data that you want to send in the request. And important that the body can be empty. A lot of times you're just visiting a web page. So that's just a GET request. So you're not really sending a body with that. And then when the server responds to you, it'll tell you the version and then a status code. A status code is kind of like telling you what happened with the request. So 200 means the request was successful, 403 means forbidden, 404 means not found, and so on. And then there's more headers, and then the response body is like the actual, HTML of the web page. Pretty basic stuff for the HTTP protocol. But what's more important about HTTP is how it like uses connections. So there are a lot of different versions of HTTP over the years. A lot of times when you're like visiting a website, you're going to visit the website and then you get the HTML of the website. But there's other content on the website you want to use, like maybe it has images on it or it has CSS or JavaScript. So there are other files you want to request from the website too. In HTTP 1.0, which is the first version, the server will close the TCP connection after sending its first response. So you ask for the web page, the HTML, the server will close the connection after sending that, and then you have to reopen a new connection to get everything else on the web page. So all the other images, each will take their own connection. This is kind of bad because there's extra overhead and latency from destroying and setting up all these connections when you know you're talking to the same server. You don't really need to like keep destroying and making new connections. You can use the same connection for everything. So HTTP 1.1 introduces persistent connections. Basically, you can reuse the same TCP connection for all requests to the server until either side closes them. And this also enables this thing called pipelining, which basically means you can send all your requests at once and the server will respond to them in order, but you're not waiting for the server to respond to them before you send the next one. So that's the image on the right called pipelining. But there's still like a problem. You could call it a problem if you want in certain scenarios, but there's this effect called head of line blocking. Basically, HTTP 1.1 requires that requests are processed in order. Basically, if like two requests are sent like one after the other, the first request has to be processed first, and then the next one has to be processed after that. So kind of like each request blocks the processing of the next ones. Or not processing, but like blocks the sending of the next ones. So there's a new version of HTTP called HTTP 2. That one has this thing called multiplexing, where now it's like a very different setup to the protocol. Now each request and response is kind of divided up into frames, and each frame has an associated stream ID. So each frame contains a stream ID in it. And you could say like one stream ID is for the first request, one stream ID is for the second request, one stream ID is for the third request. But importantly, you can send different streams like whenever you want. Like these streams can be like completely independent of each other. You can send stream 1, then stream 3, then stream 4, and stream 2. They can be interleaved together. So basically, if two requests are independent of each other, they don't like there's no data dependency or anything between them. HTTP 2 basically does not tell you what order you'll receive them in, but that allows the server to like, not get blocked by either of them. This is a bonus question, not really that important, relevant to the talk, but does this completely fix head of line blocking? Does anyone have any idea if this completely fixes the problem I described on the previous slide? Yes, Nasir?
I have a question on like 1.1 when you send head of line blocking. So let's say you send like 3 requests, do you need to like resend the request 2 and third, or it just like caches it on like the request 2, the consecutive request?
You mean like 3 different requests or 3 of the same request?
You sent one request 0. It went in and now the server is processing. You mentioned that head of line blocking just means that you send like the consecutive ones as well, and they would be processed in order. So
not necessarily processed in order, but they would be sent back in order. So as a client, if you send 3 requests, and you want like the second and third to get back to you, you have to wait for the first to get back to you, or getting the second and third, because that's just how HTTP 1.1 works.
What about the second and third request? Like even if the server was, let's say on the back end, like you were able to like process what the request asked for, but you still won't return it till you receive like the first thing is like done or the first request is sent back.
Yeah, so I think the second and third would just be put into like a queue, and then like I think they get put into a queue, and then like just you wait for the first one to finish, and then you'll send the first one, and then third. Yeah. Anyways, we'll get back to this HTTP stuff soon. Now I'm gonna switch gears a little bit and show you a challenge that Ronak over here wrote for Cyber Academy last year. Um, Basically, it's this website. Is there volume on this? Is there?
Is there sound effects?
Yes, there's the sound effects important.
I don't want to do this.
I'll just play it. Yeah, let me increase my volume.
Arlo, you should just make the sound effects yourself.
No, don't do it.
100.
Okay. Okay, so basically, if you click the do button, do Max Verstappen, you can click it 4 times and then get a Max Verstappen. But you don't want a Max Verstappen, you want the flag Verstappen. So how do you get the flag? Well, in the code it says you need 6 of them. You need to get 6 do's. Now the problem is that the code only lets you get 4 do's, right? Like as soon as you get 4, you can't click do anymore. So this is how that code works. It says if the amount of do's is less than 4 and you click do, then you'll sleep for some amount of time. I don't know why. And then you're going to increase the amount of do's. Well, the sleep is actually important here because this introduces a time of check to time of use vulnerability, also known as talk tool. Basically, if we just send a bunch of requests to do, like kind of basically all at the same time, and another thing to keep in mind that this server is like multi-threaded, so it'll like kind of process these requests like with different like in concurrently. It'll receive all these requests and it'll think that the amount of dues is less than 4 because they all kind of arrived at the same time before dues was incremented at all. Then after the small time.sleep, all of these requests will increment the do counter to 6. So what you have to do is basically just spam the server with a lot of requested dues, kind of all at the same time. This is a race condition because like there's a difference between the time of check to time of use of the variable, and in that difference, that variable could change, and that's like kind of important. This is a race condition, and this is like a very classic web vulnerability that you can exploit. So you just spam it with a bunch of requests all at the same time to do. But like, what if I change the 5e minus 3, 5 milliseconds? What if I change that to 1 microsecond? Do you think you could be able to spam it that fast? Well, probably not. So normally with the way it's set up, you can just spam the endpoint. You can probably get better results from spamming by using HTTP pipelining or, just opening a bunch of connections in parallel and like spamming them. But like I said, if we make the time delay a lot smaller, like the time of check to time of use delay to literally 1 microsecond, you probably can't do all of this because like, the server will still receive like if we're using pipelining, the server will receive all of the requests in order, or it'll try to receive all of the it'll try to send back all the requests in order, the responses in order, and as a client, we're still sending all of the requests in order. So unless like some weird stuff happens in the network, we're probably going to have too much delays between the requests for the 1 microsecond to be exploited. So now we need to come up with new cool ways to exploit these race conditions with very tight windows. And so there's 2 ways to do this called last byte sync and the single packet attack. The first one is the HTTP 1.1 last byte sync. What this does is that we're still trying to spam the server with a lot of requests in parallel. So like we open a lot of like threads on our own computer in parallel that are sending requests to the server. But when we do this, we send all the requests minus the last byte. So we don't finish the requests, the HTTP requests. We keep the last byte to ourselves for all of the requests that we want to send. And then in parallel, we send the last byte of each request all at once. Now, this is more reliable than just spamming it in parallel because now what's really like we're trying to now we just have one byte to send in parallel across a lot of requests instead of like a varying amount of bytes. So this generally improves a lot the reliability of the exploit because it's a kind of a more controlled amount of data you're sending in parallel. So basically send all of the requests to the server minus the last byte, and then you send the last byte of the request in parallel to the server. But even better is the HTTP2 single packet attack. So due to multiplexing, what you can do is kind of the same idea where you withhold everything except the last byte of each request. But now you can send all of these requests together in one TCP packet because of the way HTTP2 works. So basically, each stream is corresponding to a different request, and each of these requests are sent over only one TCP connection. So the success of our exploit literally just depends on one packet, nothing else. And that one packet won't get broken up by anything when it gets to like, the application or the transport layer. So we set aside a final frame for each stream, and that final frame contains the end stream flag. You can if you're sending requests without a body, we just put no data with the end stream flag. If we are sending requests with a body, we keep the last byte of the body to ourselves with the end stream flag. Then we send all of the other frames for each request. So this opens up basically a logical channel on the server for each request or stream. So the server thinks that it's currently talking to like, 6 or 7 different requests all at the same time, but it hasn't actually received the full amount of these requests yet. Now we send a single TCP packet. What we actually do is we just send all of the last frames containing end stream to the server. TCP will put all of these things into one TCP packet. So now the server receives one TCP packet and thinks that it has to respond to 6 or 7 requests all at the same time. But so basically we're sending it, the effect is that we've sent it 6 or 7 requests from one TCP packet, which is very helpful when exploiting race conditions. So either the last byte sync attack or the single packet attack can be used in these scenarios. You want to exploit a race condition with a very tight timing window, which is the challenge I was just doing. You want to send many requests to a server that should be processed atomically. So like if a lot of people are using a server, you want to make sure that all of your requests are like processed without anyone interrupting in between. This was important in one of my LACTF challenges last year because it was like a cryptography challenge exploiting a random number generator, and you wanted to get like clean data from the server. And then you could also just like spam a server with so many requests it causes a DOS in certain scenarios, I guess. But the cool thing about the single packet attack is that it's not really affected by network jitter or like kind of like the randomness that exists on the network when sending multiple different packets. Because again, with a single packet attack, the attack happens only after the last packet is sent. It only depends on one packet. So I think I'll demo this now. This is the code I wrote to exploit the challenge. Again, remember, we're exploiting a race condition with a window of 1 microsecond. So we have 1 microsecond to get all of our requests through at the same time. So like what this does here, let's scroll down. We want to send 6 dues, so we generate 6 stream IDs. And then we create all of these header frames and a final data frame. So header frames is like all of the initial frames of our request, and then data frame is the final frame of our request that we are withholding to send in the last packet. So over here, we send all of the frames except the last frames of each stream. And then here we send the last frames of each stream. And these all get sent in one packet. And then just, parse the response and stuff. Yeah?
Wait, so like I think like around like line 30 something. See like body 33, you see body equals
Okay, so I think this is just the library I was using. It needs a data field like Python wants a data field, so I couldn't just provide an empty body. So it's a post request. So like the library didn't want an empty body, so I just like put some random stuff there. But yeah, I'm using this library to do the attack. It's called H2 SpaceX. I don't know why it's called that, but it works. So let me show you the attack. So I have it on my terminal here. And also this only works like 1/10 of the time, but like that's good enough for CTF. The reason why is because what we're really doing is sending HTTP2 requests to like a proxy. The web server that's running the application is still HTTP 1.1. So there is still going to be like some amount of jitter in between the time that proxy talks to the actual web server. But it's still a lot better than, just sending HTTP 1 directly to the web server. So it'll work like 1/10 of the time. Oh, okay. We got the flag. Yeah. Any questions? Yeah, Nassim?
How do they fix it on like the client on the server side? Like if you want to like prevent such condition to happen?
Well, the thing is this, like, you just have to fix the race condition itself. Like the single packet attack, you can't really defend against it. That's just like kind of the intended behavior of HTTP2. So I think you just should not introduce race conditions in your code.
Did they come out with like HTTP 3 or something? Well, like
Yeah, there's HTTP3, which runs over quick. I kind of have no idea how that works, to be honest, but maybe. Any other questions? Okay, thank you.
Yeah, we'll go ahead and split up into our normal group. So we'll have to work with whatever, but like who here is going to be doing, and officers also please raise your hand so I know like the split. Who here is going to do fundamentals group? Okay, and then just make sure raise your hand for advanced group. Okay, well, what about fundamentals group outside then?
What's
There's little fewer fundamentals.
Oh, okay.
Yeah, okay. So what we'll be doing is here in the advanced group, you can stand here. In fundamentals group, we'll be moving outside. There's like some tables of breakout rooms, and there's a conference room there, and we'll go ahead and hold out there. Yeah.
I want to investigate what the